All right, so with those three pieces of information, let's go through setting up the problem. So the first thing you need to know is the rate of change is modeled by Q of t, Q prime of t, and you'll see this in your notes. And that's going to equal to 9, which again, if you guys look back up, is the rate in which water enters the tank, times, and then this is going to be the salt concentration that we have to discuss, which is the 1/5 times the 1 plus the cosine of t. That's where this comes from. It's just directly commenting on that. So water entering the tank, right, minus water leaving the tank, or the rate at which water leaves the tank with the salty concentration. And this will be Q of t up here. This is by design. And then 600 plus 3t. So let's think about where that comes from, right? So we have 600 right here. And then where's the 3 come from? It comes from the difference between 9 gallons and 6 gallons, all right? So 9 minus 6, right? That's where it comes from. So I want you to make sure you guys know that. 600 is the initial gallons, okay, that we start with. And then plus 3 times t, all right? And that just comes from the difference between the water entering the tank, the rate here, versus the rate here. All right, that's where the 3t comes from. All right, so that's our differential equation. And the initial condition is going to be Q naught equals 5. And so again, let's figure out where this comes from. It begins with 5 pounds from 0, right? So now you know how all the pieces of information are put together to make this happen. Okay, so that's it. This is our differential equation up here, and this is our IVP. All right, so if we simplify this, Q prime of t, using the equation above, what we get is 9/5. This again from your notes. And this will be 1 plus cosine of t. All right, and this is going to be subtracted from 2 times Q of t, all divided by 200 plus t. So that's what our equation will look like. And then, of course, it has the same initial value. That doesn't change. We're just simplifying the problem. Okay, so making sure you guys see this is all one equation right here on the bottom. All right, so to solve this, we get this into a linear differential equation form, and you will do the same in your final. So you move all the q terms to one side and all the non-q terms to the other side. So you get q prime of t plus, and this will be 2 times q of t, all right, all divided by 200 plus t. So again, notice we're using the simplified version here. And this is going to equal 9/5 times 1 plus cosine of t. All right, so that's the setup. So to solve this, we use integrating factors again, since we're using linear forms. So notice that, like our first problem with Bernoulli substitution, we used an integrating factor. We're going to do the same thing again, but in an applied situation. So this refers to this guy right here, right? And so we're going to be looking at e raised to the power of, and make sure you get this right in your final as well. It's going to be 2 divided by 200 plus t, okay, dt. And when you work this out correctly, what you guys will get is e, and you'll see this in your notes. It's going to be 2 natural log 200 plus t, all right? And then the e and the natural log cancel, and what we end up with is simply 200 plus t squared, all right? And when we multiply that through, what we end up with is something very extravagant, and I recommend you look at your notes. But at the end of the day, when you multiply everything through, what you're going to get is q of t, and that's going to equal 9/5 once you do all the simplification. and you're multiplying it into our original equation, which is up here, right? So you're multiplying this all into this, left-hand side and right-hand side. And what comes out of all that is 9/5 times 1/3 times 200 plus t, all right, plus sine of t, all right, and then this is going to be added to 2 times the cosine of t, all divided by 200 plus t, minus 2 sine of t, all divided by 200 plus t squared, okay? And close parentheses, and then this will be added to the constant term, which will be c over 200 plus t squared, right? So that's what happens after you multiply the integrating factor and resolve and simplify, you end up with that expression. Okay, so now that you have this, now all that you need to do is apply the initial condition and solve for the constant c. Okay, so that's what we do next. So after applying the initial condition, we end up with 5 equals q of 0, all right? And that's going to equal 9/5 times 1/3 times 200 plus 2 over 200, okay, plus c over 200 squared. And from your notes, this gave us a very large negative constant, which was -4600720, right? That's the constant we got. And so plugging everything in, we have q of t equals 9/5 times 1/3 times 200 plus t plus sine of t, okay, plus 2 times cosine of t, all divided by 200 plus t, all right, minus 2 sine of t, all divided by 200 plus t squared, close parentheses like before, but now we're subtracting the constant, which is the -4600720, all divided by 200 plus t squared, okay? So we're not done yet. We need to figure out when the tank will overflow. So how do we determine that? So how do we determine this? We have a 1,500 gallon tank, right? And so how do we determine when it overflows? So you can look at your notes to determine that, or you can look at the problem statement itself. Draw your attention back to our original expression, which said the rate at which water is entering and leaving was 600 plus 3t, right? And we set that equal to 1,500, which is the initial amount of gallons in the tank. And if you solve for t, this immediately tells you that t will be equal to 300 when it overflows. Okay, so that's how you can determine when overflow happens. So to solve the problem, then you just plug in 300, the time of overflow, to determine the amount of salt in terms of weight will be left in the tank. And when you plug it in, you get 279.797 pounds. Okay, so that's it. That completes this review of first order linear differential equations. In our next video, we'll look at second order. Stay tuned.